wherever you is, please see me, we can talk. Now, yesterday I sent an email, and I had an impression some students thought I sent this email specifically to them. If I send an email specifically to you, you know I send it to you. It starts from your name. This is a generic email, has been sent to the class. So one of my job descriptions is maintaining attendance, and when I see some odds, first I make a verbal announcement, then I make an official textual announcement, and if I need to, I'm going to act according to the policies. And this is what I wanted to mention after first exam, and I forgot. Because this is a very common case of situation when we humans read the text but don't really process the whole information. It happens to everyone. It happens to me. It happens to you. Normally it happens when we read instructions, manuals, or syllabus. And the syllabus says that in the summer, standard laboratories and discussions are combined in one new unit. So laboratories in the summer could have been shorter by 1 hour to be regular, but in that case, everybody would have been attending twice a week, 1 hour discussion session, because the total time has to be conserved. And of course, BU offers other regular classes when discussions and lab are separated. In that case, the lab are shorter, but the total time still the same. Now, question, please. This picture comes from yesterday. It describes a situation when an object is released from rest, like this. And it's moving periodically, left and right, left and right. This situation is different. That means we did this. We start stopwatch, and at the same time, when the object is at the equilibrium location, we kick it. And it starts moving. So again, periodic motion with the same period, the same frequency, the same angular frequency, and if we're accurate enough, maybe even with the same amplitude. So the question basically is, does it mean we should use the same equation? Why do I know that this case and this case should have the same kinematical variable, same period, same frequency? Because if you remember, angular frequency, period, regular frequency related to two variables, k, spring constant, and m, mass. So if I don't change anything with springs and masses, I don't affect the period, I don't affect the frequency, I don't affect angular frequency. So what do you think? You still have time to enter, but what do you think? What equation would you use when an object is kicked when it is initially at equilibrium?
Could be sine if it's at equilibrium.
Of course. It's not a tricky question. It cannot be a cosine. It is kind of handy, useful to remember that, oops, again, cosine of 0 is equal to 1. Well, negative cosine of 0 is equal to negative 1, but sine of 0, not theta, 0 is equal to 0, or negative sine of 0 is still equal to 0. And we never can use tangent. Tangent is not a limited function. It goes from infinity to infinity. So this helps to choose if initial location is not 0, but initial velocity is 0. That's what we say an object was released from rest from a stretched position. We got to use a cosine. Yeah. But if initial location is 0, and we mean that 0 and equilibrium same things, in that case, we got to use a sine. That's it. What sine, plus or minus, or what cosine, plus or minus, that also depends on initial velocity, how it moves to the left, to the right. So here the answer is either plus or minus. Well, okay. This is my experiment. The initial velocity points to the right. Yeah, I made it move to the right. So the initial position was 0, but the initial velocity is positive. That information should be sufficient to make a choice between using a sine omega t or x equals negative a sine omega t. Well, actually, just for the kick. First of all, so it starts from here. In a fraction of a second, where is it? To the left or to the right to the origin? Now we have to close our eyes and imagine how it moves. Equilibrium in a fraction of a second. Where? To the right. Right means positive. So in a fraction of a second, it actually should be here. So we go like this, like this, like this. For velocity, we should start either from positive value or from negative value for the graph for the velocity. If it starts initially traveling to the right, positive, so it should start from this position, and it should go like this, etc., etc. So for the velocity, the graph should have this form: maximum value when an object travels making simple harmonic motion. Everything has some maximum displacement, maximum speed, and that's supposed to be cosine. And they have the same period, the same angular frequency. And for the acceleration, we always can write this equation. This is a Newton's second law for simple harmonic motion. Yes?
Those graphs represented kicks from equilibrium, right?
This graph and this graph represent position as a function of time and velocity as a function of time when it was kicked, not released from rest. Pushed, yes. Oh, well, we would have to kick it in the positive, in the opposite direction, to the left.
Oh, so it's just directional.
Yeah, and everything flips. We just need to look at the numbers we read on the ruler. The 0 is placed at the equilibrium. So if I kick it and it starts traveling to the right, the graph should start from 0 and be positive for a certain time. So first quarter of a period, it stops to a point of the return. Second quarter of a period, third quarter of a period, fourth quarter of a period, one whole period, 4 quarters. If I kicked it to the left, so it should start from 0, the graph of the position, but the next number should be negative. We should read negative numbers for a while. Then it reaches limit, then more negative numbers, reaches 0. We have to be careful around you today. So, just imagine, like you're watching a movie, but that movie also has a ruler, and you read in numbers. Okay, so, we just did this. Let's do it for another, if initial velocity was to the left. So let's say we kicked it, and V initial points I don't know, 2 axes. And V initial points to the left. So in that case, at t equals 0, position is 0, but the next, in a fraction of a second position, should be negative. So, and now we know we should continue drawing the graph like this. This is a graph, an abstract line. The top picture might represent a photograph. We can actually see a ruler and an object. And in this situation, we should write an equation, the motion equation, like this. But the velocity, now it should start from a negative value. Initial velocity is not 0, but points to the left. And with the same period, a period has 4 critical instances. So when the displacement reaches maximum, the cart stops, 0 velocity. When the object travels through the equilibrium, it travels as fast as possible, then stops again as fast as possible. That's what is happening. All right, let's solve this problem. This is not a question. So please read and try to draw a picture and try to sketch a graph for the position as a function of time. What is happening here? Visualizing and graphing usually is helpful for any situation. So, did we kick it or did we release it from rest? If we kicked it to the left or to the right, if released from rest, the initial position was to the left, to the equilibrium, or to the right, to the equilibrium, how did it move immediately after it's been released or kicked? These are questions we should answer to themselves. I still see some people who make the same mistake they've made on the exam. thinking. It has to be automatic movement, no thinking. Trust your guts. So you can also actually write the motion equation of your choice now. Again, you have to choose between a sine and cosine, between a plus or a minus. Oops. So I always like to draw at first when nothing is moving equilibrium. So I would see where the equilibrium is. That's my equilibrium. So now an object, a block, has been moved to the left. So first of all, if I don't know what left means, that's it, no physics. What I do. Now, released from rest. So again, the text has many words, but some words always are more important, more informative. Initial speed is 0. So now, natural question, if I let it go, how would it move? In which direction? What do you think? To the right. Exactly. How do we know? Common sense, life experience. Yes?
Does it matter which side you have this from?
No. Technically, I'm a right-handed person. This is how I just was drawing it for a decade. We can do it differently.
So if the problem doesn't specify, we can pick if we want.
Yeah. Because it doesn't affect the equilibrium. It doesn't affect anything, actually. I just need to remember that the axis still points to the right. And this is still my equilibrium. And this is my location, which is to the left, to the equilibrium. And if I let an initial speed is 0, the spring is compressed here. So the force, restoring force, wants to move it to the right. The string is stretched here, so the restoring force still wants to move it to the right. So, see, so x equals, these are our, well, first of all, there is amplitude, there is omega times, and we have to choose between a plus or a minus, between cosine or sine. These are choices we need to make in life sometimes. So what usually helps is to start sketching that graph. Does it start from 0? No. Does it start from a positive number? No. It starts from a negative number. That's it. The rest goes automatically. It has to be a simple harmonic function. So it has to be a negative cosine. And we need to write two numbers. One is for amplitude, second is for angular frequency. For the amplitude, it's 10 centimeters, but we cannot use centimeters, right? So we have to convert centimeters into meters, 0.1. And by definition, again, the amplitude is the magnitude of the maximum displacement, so it's always positive. And this we just have to remember or use equation sheet. What is it, 10? Square root of 10 over, well, grams. We, again, have to convert into kilograms, 0.1. So 10 radians per second. So technically, this is what's happening. Or this. If we compress now, still symmetry. You look confused, no? Okay. It's your natural look. Mine too. Question? So let's take this object. We make it move, or this one, we make it move. Yes?
Can we do velocity for the previous question?
I don't know. Can you? Go ahead. Well, you have to be here. You said you can. Go ahead. Thank you. I can relax now. You have to say something.
Okay. Well, first I'm going to trace out what I believe are the important points of the graph.
Well, the most important thing you believe.
And then, if I remember correctly, at the 0 points of the x, it should be the maximum of the velocity.
Absolutely. The question is which one?
Exactly. Sorry.
That's okay. Oops. Oops. You broke it. Don't worry, we'll fix it. Eventually. All right. I think maybe you you press the button and it reacts to something. Yeah, sometimes I do the same.
Okay. So initially it's going to be at 0. See, what I'm having problems is figuring out whether it be positive or negative first.
So when we let it go from this position,
It's going.
it was traveling to the right.
So it's positive.
So even when it was traveling through the equilibrium, at that instant, the velocity was directed to the right.
Yeah.
So a quarter of a period after it's been released, the velocity has to be positive.
Yes. Okay.
You place one dot in a half of a period, velocity has, and that will tell you the whole graph.
Okay. All right.
Thank you.
Thank you.
It's not very often I can ask a student to the screen. If we had a blackboard, I would do it much more often, because people don't believe me, but they tell you what to do. You just have to listen. That's it. Question? Yes. Question? Yeah.
What about for the velocity equation?
Well, what function should we use for this curve, for this sign? So there is maximum speed. There's always a limit for everything which oscillates, and we should write sine omega t. And this maximum speed is related to amplitude and angular frequency by this equation, which we will prove today, hopefully, if we have time. Yes?
The other day when we were writing it, we said it's equal to negative.
Well, it probably was a different graph.
Okay, so it's just,
It depends on the actual graph.
okay, so we just go with the initial velocity.
Yes, and yesterday, one slide or two slides had a link to online graphic plotter. I strongly recommend to play just to get the feeling. If you enter a function, see how the graph goes, So it gives you some connection between an equations and lines which represent the graph of those equations. So you wouldn't have to think, you would know this graph, this equation, this graph. That's a time-saving, basically, like a hint. And for acceleration, if we want to, acceleration is much easier than velocity. It doesn't require thinking. It requires straightforward application of a Newton's second law, which says acceleration equals negative omega squared times x. So wherever x is equal to, you flip it and maybe squeeze or stretch. So for the acceleration, it's always opposite to x. Everything negative becomes positive, everything positive becomes negative. And they all have exactly the same period, they all have exactly the same frequency, they all have exactly the same angular frequency. All right, so let's go back to this question. And let's actually check if we assign. Oops. Let's start with assign. I do have enemies. So that was a question about kinetic energy, question number 3. What do you think is happening, if anything? Okay, keep answering. We just have 16. So this is the question. We are looking at an object making a simple harmonic motion. It travels back and forth, back and forth. So kinetic energy, Ke, kinetic energy. Well, at this point, we need to write an equation. What is an equation for kinetic energy? Absolutely. It doesn't matter what kind of a motion is happening. The term kinetic energy in Newtonian mechanics is reserved for this expression. So what does it say? So if you want to make it negative, what numbers would you use? Like for the mass? Well, just pick a number for the mass. 10. And what number would you use for velocity? Well, you want to make it negative. Negative 5, perfect. So now we can actually calculate that energy. Kinetic energy will be equal to 1/2 times 10 times negative 5 squared. Still positive. So this is a review question. We know kinetic energy is never negative because of this, because we square, right? So it's always positive. If an object is at rest, it might be 0, so nothing new. But more importantly, it changes. If it changes, that means we can apply the same old-fashioned, well-known work kinetic energy theorem. The change in the kinetic energy is equal to net work. But if, well, we're looking at the horizontal motion, normal force doesn't do any work. Exam 2. Gravity doesn't do any work. There is no friction, we neglect it. The only force acting on this object is elastic force, so net work is just the work done by that elastic force. Unfortunately, elastic force is not constant. We cannot apply directly the expression we used for the work done by a constant force. However, not a problem. We can break the motion into smaller parts. We can treat each individual part as a motion with constant acceleration, and then we can add them up, and the result is this. We've seen similar expression before, a difference between two. That expression was for the work done by gravity. And we also had an expression for what we called gravitational potential energy. Now, we have a very similar situation. This is the work done by elastic force. And this expression has a name, elastic potential energy. So we can always use both expressions. Now, I am stretching this spring. The spring does work. A work is a number. For any number, we can have only 3 options. A number might be positive, 0, or negative. Right? So when I am stretching the spring, the work done by this spring is, you should finish the sentence, positive, 0, negative. I am stretching the spring. The work done by the spring is negative. First of all, I am doing positive work because my hands do work. My hands do work against the spring. It's a similar situation when my hand does work against the gravity. Gravity does negative work. But of course, this equation tells us the initial, well, let's say it starts from equilibrium, initial length is 0, and elongation, there is no elongation. If we start from equilibrium, same thing. And when I make it longer, this is not 0 anymore, 0 minus not 0, negative number. When does spring do a positive work? Well, for example, when I release it from a stretched position, basically every time when a spring makes an object move faster, speeding it up, the spring does positive work. When an object moves slower because of the spring does negative work. So if I let it, so right now, if I let it go, it moves faster, slower, yeah? Speeding up, slowing down, speeding up, slowing down. So the spring does positive, negative work. So let's talk about this special case. Where is it? Here. Start from equilibrium, move from equilibrium, start from rest. It doesn't affect anything. It's just something we're already familiar with. Time. Velocity starts from rest. Go like this. And that's it. Now, kinetic energy. We need to square speed. So, when the speed was negative, we square it, we make it positive. When the speed was positive, we square it, it remains being positive. This is the graph for kinetic energy. That's it. So it's never negative, but you can see the period of kinetic energy equals a half. One total period for the motion equals twice periods for energy, kinetic energy. This is one period, which is 2 pi over omega. Here, this is the period, but here, this is the period. It repeats itself twice faster. Now, what about potential energy? Well, we can draw the graph for the potential energy using x squared. So, when location is at the maximum, potential energy at the maximum. When we go through the equilibrium, potential energy is 0. But, again, x is squared in that equation. So, when x is positive, x squared remains positive. But when x is negative, x squared again is positive. So, this is the graph for potential energy. And that will be the period of the potential energy. And we can see it's equal to, again, a half. So kinetic energy and potential energy have the same period, which is a half of the actual period of the motion. Now, potential energy of what? This question depends on the interpretation. Some people say it is just potential energy of that spring. We stretch or compress the spring. Some people say it's potential energy of a ball on a spring. Some people say it's potential energy of the system, spring ball system. For us, it doesn't really matter. Technically, it is a potential energy of the system. This is kinetic energy of the ball attached to the spring. And this is potential energy of the compressed or stretched spring with the ball. So, but people use the slang, kinetic energy of the ball, potential energy of the ball, meaning of the whole system. The ball without spring doesn't have elastic potential energy. Any questions? Well, potential energy and kinetic energy also changes with location. So please, what do you think? How would a graph for kinetic energy as a function of position look like, or the graph for a potential energy as a function of position. These graphs represent how energy changes with time. But we also can say something about how energy changes with the location, with the space. Again, we can always look at our specific example. An object starts from rest, from a stretched position, and that's how it's moving. So this is exactly one period. Oops. Equations. Kinetic energy is equal to mv squared over 2. And now we know elastic potential energy is equal to spring constant x squared over 2. And I would start from potential energy. This function looks familiar. Is it a linear function? No. It's a parabola. So the motion is happening between two limits. When x is 0, x squared is 0. When x reaches maximum, energy reaches maximum. So a parabola. This is elastic potential energy maximum. And it should be equal to Ka squared over 2. But what about speed? When the speed is at its maximum, when it's moving, the maximum speed is reached at a specific location. What location is that? Equilibrium. It stops at one limit, it stops at another limit, and it reaches maximum at the equilibrium. So at x equals negative a, it should be 0. At x equals a should be 0. It should reach maximum at the equilibrium, something like this. Well, I've got slides, graphs, and now we can say, since we have no friction involved at all, we neglect any friction, we can also write a law of conservation of mechanical energy using our standard form. Mechanical energy, which is kinetic plus potential, has to be conserved, has to be the same. And this is a neat example of a combination of physics and math. So again, if we use our special case, if we calculate the expression for potential energy as a function of time, if we calculate the expression for kinetic energy as a function of time, this is cosine squared. That's exactly what we saw, 2 bumps up. This is sine squared, again, 2 bumps up. But if we add them up together, and we use a very fundamental expression, which is Pythagorean theorem. Cosine squared plus sine squared always equals 1. Turns out we get the constant in the end, which is, again, a mathematical expression of the law of conservation of mechanical energy. Potential plus kinetic remains constant, always, neglecting friction. Question. You take a 250-gram cart. Actually, this is what it is. This plastic cart weighs exactly 250 grams. You attach it to a spring. You move it away from equilibrium position. You let it go. It travels back and forth, back and forth, back and forth. You have a, let's say, ultrasonic motion sensor. And you know what ultrasonic motion sensor does. It measures position as a function of time, velocity, acceleration. So you can read on the screen that at the equilibrium position, when it travels through, the speed of the cart is 4 meters per second. That's what you know. So using this information, you should tell how many joules is stored in the maximum potential energy. When potential energy is reaching maximum, how many joules should be stored in it? If it's 1 joule, 1, 2 joules, 2. And of course, this is when you need to do something with your hands, not with your brain. First, you should calculate what you can calculate. That's always the case. You look at the numbers given to you, and you don't ever think, how do I find the unknown? No. You ask, what can I do now? And you do it. So, what can you find now? If you know the mass, if you know the speed, what can you find, gentlemen? Kinetic energy, absolutely. If you can, you have to. So calculate kinetic energy. Just pay attention to units, right? There is one unit which you need to convert. What unit do we need to convert? Grams to kilograms. So 250 grams divided by 1,000, 0.25 kilograms. What did you choose? Well, you have found the kinetic energy. Why did you say that maximum potential energy should be the same? Absolutely, that's the answer. So we know that for any two instances, for any two locations, mechanical energy of this system has to be conserved. So here we need to relate two locations. Yeah. Well, so this is the graph for the position as a function of, let's say, time. The graph for the velocity, so it starts from 0 and it's negative. So here kinetic energy is 0, potential energy is max. Here, that's a V. Kinetic energy is max, but potential energy is 0. So what do? We say mv initial squared over 2, or doesn't really matter which is, let's call it 1 and 2, should be equal to u2 I mark them differently. mv2 should be equal to u1. Yeah. This is my point number. I chose to be this point number 1, and I chose to be point number 2. Doesn't really matter. This is u max. This is actually kinetic energy max at its maximum. And that's actually also equal to total energy, total mechanical energy. Same number for all of them. And that's supposed to be what it is. 0.25, it's 1/4 times 4 squared divided by 2. Kinetic energy, mv squared over 2. So all these numbers are equal to 2 joules. The total amount of energy in the system, yes. These graphs, so one is a graph for position, second is a graph for velocity. But these graphs describe what is happening with time. So if I want to describe what is happening with x, I need a ruler. And on the ruler, that's equilibrium. And this is, let's say, x max. Here at the equilibrium, there is no potential energy. This is what I call 0.2. But kinetic energy here reaches maximum. Here, it stops momentarily. That's what I called 0.1. Let's say I released it from that and then travels toward the equilibrium. Here, at this location, so when I say here, I say at this instant. When I say here, I mean at this location. So instant location, and at this location, potential energy reaches maximum. The string is stretched as much as possible. But here, it stops momentarily. So here, what I called kinetic energy initial, first, will be 0. So in my mind, I've selected 2 points or 2 instances, and I called this first, right? And which I called first. Now I also need to divide the line. So this belongs to the graph above the line. This belongs so 0, right? This I called position number 1, and this I called position number 2. Or I could have called this the first instant, and this the second instant. We just need to remember that at the equilibrium, no potential, maximum kinetic. At the maximum displacement, no kinetic, maximum potential. But if we add them up together, we always get the total, which is always constant. Okay, I wanted to prove this, so let's do this. Again, we just need to apply the same law, but without numbers, algebraically. Let's set this to equilibrium. Let's set this to maximum displacement. So what does it tell us? At equilibrium, mv max squared over 2 plus 0 should be equal to 0 plus k a squared over 2. That's it. So 2 and 2 getting canceled. V max becomes equal to square root of k over m times a, square root of a squared. That's it. So this is just a definition of maximum displacement. This is Newton's second law, and this is just a specific this expression comes from a specific point when location is at the maximum. We didn't know this yet. Now we know. And there's a slide. Question. We've got the motion equation. And now from this motion equation, we can extract all information. Everything. Let's start from a period. So you should just copy the specific equation, the equation which is given to us. The rest already should be a part of your equation sheet, or you maybe remember some equations. And this is everything we can calculate, we want. It will take too much time, but technically this is what we can calculate, and we have found already before such variables as Vmax, Amax. So we can add energy and a couple more questions, but we have to start from extracting the information about very specific physical variable, which is not period, which is related to the period. So if we have a motion equation, first, of course, we know the amplitude. And the second variable which immediately goes from the equation is what? What do you think? Again, this is the equation. This is the amplitude. What is the next variable which? Omega. Omega. So this is what I do. Omega equals pi. Yes or no? You see? You're paying attention.
Well, I answered that.
But now you know. That's how people learn. There's nothing shame in making mistakes. Sticking to the mistakes is not good. So omega, how do we get it? Well, the easiest way is to rewrite the equation in the standard form. The standard form has a number, a function, and then in the standard form, a variable t should be the very last. So if we rewrite it, the coefficient will be not a pi, but pi over 2. So omega equals pi over 2. That's it. So now if we know omega, the period equals 2 pi over omega 2 pi over 2, 1. Yes or no? I've seen that. So what do I have to write?
Just 4.
4. Finally, it's Wednesday, the first time I have to write my perfect number. 4. Seconds. Now, where else can we calculate? Well, okay, Vmax omega A. I'm not going to plug the numbers. A max omega squared A. K. We know the mass. So we also know that omega should be equal to square root of K over M. So to get K, that should be omega squared times M. We just keep applying equations for everything we need. So where else? Well, frequency is 1 over T. Maximum force. Well, we are looking for the magnitude. We can apply, well, actually just delta x max. Maximum displacement. When the object is at equilibrium, x is 0, force is 0. Force changes from 0 to maximum, back to 0 again to the maximum. U max, not U mass, U max, 1/2 Ka squared. That actually will be equal to automatically to kinetic energy maximum because they are equal, or total energy because it is conserved and equal to maximum values. So this part is very simple. Now, find different quantities at different times. Well, that requires an equation. Yeah. Well, this equation is given. If we need an equation for velocity, we got to go back in time to see a set of equations. Velocity. First of all, we need to imagine what should be happening to this guy. It's very important. So we have to sketch a graph, x time. To sketch a graph, we need to know the properties of sine. It starts from 0, and it's initially is positive, goes back to 0, negative. This is one period. What does it mean for the velocity as a function of time? It starts from 0, sine, which means we kicked it. In which direction? Initially, it's been traveling to the region of positive axis, which means to the right. So this is how we kicked it. So initial velocity was positive. It wasn't 0, it was positive. Eventually, the velocity goes to 0, and etc., etc. And we look at this curve, and we know it is not a sine anymore. It is a cosine. So the equation is V max cosine, same omega. They all have the same omega. And we know that V max, because it was on the previous slide, equals amplitude times omega, which is pi over 2, or wherever it is. 15 point something divided by 2, 7 point something meters per second. And with these equations, now you can calculate everything at any instant. You just have to plug a number, and remember, these are radians. The equation for kinetic energy, mv squared over 2. The equation for potential energy, kx squared over 2. That's it. This part might be a little bit trickier. We are given a location. We have two approaches to extract information from a location. One, we can find the time. Second, we can use conservation of energy. So for example, at x equals 1.25, 1.25 supposed to be equal to 5 times the sine of pi over 2 times that particular time, wherever it is. Hat. It's not a general running variable, it's a specific instant. Now we have to solve it. This, well, requires some trigonometry. 1.25 divided by 5 equals what? Hmm? Point to 5. 0.25 is a quarter. I like it's a 4. Another opportunity. And that's supposed to be equal to the sine of this particular time. Now you're going to take inverse sine of that, right? Whatever it is. Pi divided by 2 times this particular instant should be equal to the inverse sine of a quarter. Let's just solve it. This will be equal to 2 divided by pi times so what is the number? Roughly about the point something, I guess. Anyone? I just heard from me. See. Plus my calculator is in degrees. I have to convert it to the radians and do this. 1/4. If your calculator is in degrees, if you do this, you get degrees. But we need radians because we use radians for, so I don't know how to switch my calculator to radians. So someone has to tell me the number, whatever it is. I
got 0.16.
I like it. So where is it? Well, we know the total period equals 4 seconds. So each quarter equals 1 second, 0.16 somewhere here. And what did we find? This is the amplitude, the maximum displacement. A half of a displacement is here. This is a quarter of a displacement is here. So it's reached somewhere here. But we need to remember it doesn't happen only once. It happens again. So it's not just one answer. It could be more answers. And then it happens again. And again, and again, and again. But your calculator gives you only one answer, always, the smallest one. So if you ask for well, within one period, in this particular case, you see you have it happen 3 times. So in general, you may add 2 more numbers. Now, let's say again, just, so that's it. We have solved the problem. I just want to make some general comment. Let's say we have, again, a standard special case. The graph looks like this for a quarter of a period. What does it tell us? Well, first of all, the motion, this motion, is not the motion with constant acceleration. Acceleration changes. It is not the motion with constant velocity. Velocity changes. If we had a motion with constant velocity, the graph would look like this. It should have been a straight line. For the straight line, a half of a time means a half of a displacement. We see it's not true for this motion. When the object is at a half of the amplitude, it's reached actually somewhere later than a half of a period. When the object is at the half of a period, it is actually closer to the initial location than a half of the amplitude. So graphs might be sometimes very informative. Without any calculation, we can make an estimation about a location or about a time. Now, we have studied this system because all other systems mathematically equivalent to this. If you have a cart with two springs, you can always manage to find a spring and an object with so specific masses and constant that it would have the same period. That's it. So mathematics will be the same for all possible systems. For this one, for this one. And in particular, for the vertical spring, no question. You had a question? Or are you stretching? Good. Everybody should stretch. So, not a question, because the answer is given. We need to remember that every time when we have a chance, and we almost always have a chance, to choose zero at the equilibrium, we have to take that chance. Why? Because in life, when we have a chance, we have to take it. So this is not the right location for zero. This is the right location. And now for the vertical axis, zero, positive-wise, negative-wise, it makes a simple harmonic motion with the exactly same equation, which is no different at all. It's just instead of a letter X, we use a letter Y. But to calculate frequency, period, we use exactly the same expression. Nothing different. The difference might only come when we need to talk about energy, because now there's also gravitational potential energy. Next step, the pendulum. We don't need to do this mathematics, but we can, because it's all about torque. Rotational motion, there's a torque due to gravity. In general, for something like this, the period depends on mass distribution, so the equation involves the moment of inertia. But if it's a very simple object, small ball, the moment of inertia is just mass times the radius of a circle, and the radius of a circle equals the length of this string. So for the simple pendulum, this is how we can always calculate the angular frequency. And again, this is not a question, because I have no time for that. But the answer is obvious. Do you see mass in this equation? No. So the period of the motion of a simple pendulum doesn't depend on the mass. See? Small ball, heavy ball, exactly same period. What does it depend on? On the length, L. If we increase the length, we decrease the period. If we decrease the length, we increase the period. Short should move fast, long should move slow. Oops, this guy. That's it. In fact, here we have a string, short string, which is 4 times shorter than this one. So this ball has a period twice smaller than this one. No mass, period the same. Length matters. And we're done. And that's where we start tomorrow. But today, before you leave, I want you to do the thing. You know what thing to do.
Can I ask you why it was only 1.5 as opposed to?
Because of square root. See?
Oh, you have to square the thing.
I'll be back.